All right, all right, all right. This time we're going to estimate a population mean. So in 9.1, we did estimating the population proportion. And so we kind of need that information in order to work with our population mean. Now notice this is estimating because the same situation. We have a point estimate is where we're starting. So I wrote right over it, didn't I? Here we are with the population mean or the sample mean. Literally the same, I don't know, symbols. That's the word I was trying to collect out of my brain here. The symbols that we've been using all semester long. Mu is a population. X bar is the sample mean. All right. So that's kind of what's happening here. So in the previous section, we did a population proportion, and we were looking at that in the sample proportion, right? And that was our point estimate. This instance, because we're talking about means, that is our point estimate. That's in the middle. And then we're going to have a margin of error around that. But when I'm talking about a mean, then we have to get a better idea about what we're talking about with a mean. All right? So the website, fueleconomy.gov, allows drivers to report the miles per gallon of their vehicle. In this data, from Table 2, we show the reported miles per gallon of a 2014 Toyota Camry for 16 different vehicle owners. Obtain a point estimate of the population mean. So a point estimate here of this population mean. So there are more than 16 Toyota Camry drivers. So we are going to be looking at the mean, but because this is a sample, we're using the symbol X bar. Now, you know how to find a mean? You find a mean the exact same way you find a mean ever. You add them all up and divide them by the total. So we'll take 25.9 plus 27.2 plus 27.4 plus blah, 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 blah. 27.2, which is the bottom one. Divide it by 16. Now plug all that into your handy dandy calculator. What do you get? I'm going to do this top part here and get all those added up. And I come up with 449.6, and I'm going to divide that by 16. How are we doing? 28 point, just go one decimal place will be fine. 28.1 miles per gallon. That is our point estimate. All right. So that is our point estimate of mu, because we're taking what we're looking at here for our sample, and then we're estimating the population that goes with it. All right. Okay. All righty then. So the next thing we're going to talk about is our students' T distribution. Now, I'm going to give you some backstory. So just grab a cup of coffee, grab a cup of tea, right? Whatever it is you drink, and enjoy this sweet little story. So here's really what's happening. When we're talking about a mean, all right, back in the last section, we made sure that it was normally distributed. When it's normally distributed, I can use those z-scores that we were looking at, right? So I was looking at the z-scores. Well, turns out it makes a difference if I'm talking about proportion or if I'm talking about mean. Big shocker, right? Because it's two separate things. So here is how we play this out. Here's our story. So this is in your textbook, but I'm just going to read this paragraph to you because I find it interesting. In the early 1900s, William Gossett worked for the Guinness Brewery. Gossett was in charge of conducting experiments at the brewery to identify the best barley variety. When working with beer, Gossett was limited to small data sets. At the time, the model used for constructing confidence intervals about a mean was the normal model, regardless of whether the population standard deviation was known. Gossett did not know the population standard deviation, so he simply substituted the sample standard deviation for the population standard deviation as suggested previously. So it says by Formula 1, but I'll show you what that is here in just a second. While doing this, he was finding that his confidence intervals did not include the population mean at the rate expected. So he's seeing discrepancies, right? That's what we're figuring out here. This led Gossett to develop a model that accounts for the additional variability introduced by using S, which is sample standard deviation, right, in place of sigma, which is population standard deviation, when determining the margin of error. Guinness would not allow Gossett to publish his results under his real name because, well, obviously Guinness is very secretive about its brewing. That's what companies do, and Guinness is super popular, right? And it's been around for a very long time. But did allow the results to be published under a pseudonym. Gossett chose student. So we have students' T distribution. All of this, so this next piece here and this whole section is based on the students' T distribution because this is how discoveries and innovations and all of the awesomeness that we see in science and statistics and math, it's because there was a need, right? All inventions, there was a need. Well, this William Gossett, he's doing work. He was doing his job. He was doing his statistics job. He just happened to be working for Guinness, right, at the time, but he's doing his job. He wants to be accurate. He wants to do his job well. So what does he do? Figures out a way to be more accurate so that he could be more successful in his job. All right. But notice at the very beginning, what does it say? Gossett was in charge of conducting experiments at the brewery to identify those. When working with beer, Gossett was limited to small data sets. And that's what threw this off. Remember, we always talk about the law of large numbers. The more data we have, the more accurate it is, the closer it is to the normal, right? All of these things we've been saying this whole time. Well, what happens when you have small data sets? And you be working with the mean, boom, here we are. Suppose that a simple random sample of size n is taken from the population. If the population from the sample is drawn follows a normal distribution, the distribution of T here is equal to X, that's an equal sign, X bar minus the mean, so sample mean minus the population mean, right? Divided by the sample standard deviation over the square root of n, right? So that is our sample. Have we seen these formulas before? Yes, we have. This is our sample mean for standard deviation, right? And then this is our mean, this is mean. So we're working in terms of z-score. We are now looking at t-score. So my data minus the mean over the standard deviation. Remember how I said if you just know the basics of it, you'll be able to get everything. And we're just going to vary that a little bit. This has to be varied simply because anytime I have these small sample sizes that we're looking at, in particular this, when I'm talking about mean as my data value, it makes an impact. So this follows students' T distribution where n minus 1 degrees of freedom, where X bar is a sample mean, S is a sample standard deviation. All right? Okay, so the interpretation of the sample standard errors of X bar from the population mean turns out the shape of T distribution depends on the sample size. So your sample size makes a difference in your standard deviation. Your sample size makes a difference in mean. All right, now let's talk about degrees of freedom here for just a minute. So notice this says n minus 1. So my sample minus 1 is the degrees of freedom. Here is, is an example. It's the best way to say, to help you catch what I understand, get out of degrees of freedom, and hopefully you can understand it. So assume you have 5 pins of different colors. All right. The first person wants to borrow a pen. So they have 5 choices, right? The next person wants to borrow a pen. You have more choices. You get all the way down to the 5th person that wants to select a pen. Do you have any choices left by the time you get to the 5th one? No. So there is no freedom in this last one. So that tells me n minus 1, taking it to where you're not just left with 1, right? So if I have 17 minus 1, it gives me 16. That means I have 16 degrees of freedom because that last one has no freedom. You're stuck. You see what's happening there? Okay, so this is saying, given my sample, I want to make sure that I have choices. And I don't have a choice when I'm down to that very last one. So we're saying n minus 1 will give me those degrees of freedom so that I have those choices that go with that. All right? Okay, and we'll see how this all plays out as we, continue through this section.